Okay, so we're going to talk about rocks again today. Last time we talked about igneous rocks. Today we're going to do sedimentary and metamorphic rocks. All right. On your It's Learning page, there's the Rocks 03 Rocks Quiz 2, and it goes right along with this. So if you've got that open, I'll try and point out when you're going to want to write some things down. So this picture was taken right here in the U.S. That's me sitting on the edge of a cliff. Can't quite tell how far down it is. It's a good ways down. That's actually just outside of Las Vegas. That's in, I think it's called Red Rocks State Park. It's really beautiful. There's all this red sandstone, and this is sedimentary rock, and you can easily actually see that just by looking out there. You can actually see that it's layered, like there's lines of this stuff. So sedimentary rocks get laid down in layers on our surface, and that's one way that we're going to identify them down in lab. Okay, this is a type of rock known as a clastic sedimentary rock. You can see where it's weathered, where some of it's worn away, and like it's kind of slipping down the slopes here. But that was a beautiful, beautiful hike up into that stuff. The red, as opposed to the white, contains more iron, so it looks redder color than the white stuff that's on top of it there. So let's dive in here. Sedimentary rocks. They form through a process of weathering and erosion, which is when the rocks get broken down into little bits and then redeposited somewhere else. And then they have to lithify or harden back into rock. So you need a specific environment to do this, but essentially you need erosion and deposition to work. Okay, so erosion is the weathering and removal of rock. Deposition occurs when it gets put back down. And there's lots of things that cause it to get put down. Right? Gravity is the big one. But things like water, wind, ice, those things all move and then deposit sediment someplace else. The next step in that process is called compaction and cementation. So this is the lithification part that I was mentioning. In order for loose regolith, loose stuff, to become new rock, you have to have it get compacted. You have to remove all the little air pockets in it. So in a typical environment like outside of our school here, like you think of the dirt that's underneath the ground, and the sand and the rocks and things that are down there, if you were to start digging a hole, that stuff's never going to become rock. We could wait around for 1,000,000 years, and unless some other geological changes happen, it's not going to turn to rock. First of all, it's not deep enough to have enough pressure on it to compress it enough. And secondly, you need something to cement it all together. And that really happens at the bottom of like oceans, at the bottoms of lakes, where water can actually move through those little pore spaces, and it will redeposit kind of cements that have dissolved into the water and harden the whole thing back together. So not every bit of dirt that you see outside is definitely going to become a rock. It's rare circumstances that will produce rocks. So we classify sedimentary rocks into two big groups, and these are the ones you're going to write down in your lab or in your questions here. So if you're looking at question 1 right there, it asks you to name the two main groups of sedimentary rocks and explain how they form. This is the first one. So don't go forward yet, but get the first one down. The first group is called clastic sedimentary rocks. Or if you just want to write clastic, that's fine. The way to remember this is clastic sounds like bashtic, like bashing something. So clasts are little tiny pieces of stuff. That's what a clast is. And these are rocks that are made up of little tiny pieces of stuff. How about that? They are the rocks we were basically just talking about that are weathered and broken apart and then hardened back together. Okay. So you can jot down that clastic are composed of weathered bits of rocks and minerals. So other broken pieces of other rocks is what these are made up of. And that's enough. Okay. We do classify them by the size of the things that make them up, the size of their clasts. We also look at what type of cement's holding them together. Some rocks that we'll look at down in lab will be shale, which is some really common stuff. It's very flat. Sandstone, which looks a lot like sand. It's hard. And conglomerate, which looks like pebbles that are all welded together. So we basically classify this stuff on the size of its clasts, the size of its chunks. Anybody still writing on that one? Okay, I'll give you another sec. Just get down this first bit here. That's really what's important. Here's a picture of some shale. It's actually got a fossil in it. Can you see the fern here, the little fern frond? So sedimentary rocks, particularly clastic sedimentary rocks, can oftentimes contain fossils. That's where we find a lot of fossils, because they're, broken up bits of stuff that have hardened together, so things can get trapped between there, especially if it's very fine, like a shale. Here's a conglomerate. We'll look at these in lab as well. If you notice, you couldn't see the size of the grains in the shale. It's actually made up of stuff that's so fine and so small, it would be essentially clay if we were to look at it under a microscope. So it's very, very fine little particles, which is why it preserved the leaf so well. In terms of the conglomerate, it's made up of big, chunky pebbles mixed with other stuff. So you've got a conglomerate if you have nice, big, rounded pebbles in there. Chance of preserving a fossil, and that's a lot less because those pebbles would have destroyed it more than likely. Right? But it's possible. The other group of sedimentary rocks that you're going to write down to finish answering question number 1 is chemical sed rocks. So jot down chemical sedimentary rocks, and these things form from the dissolved substances precipitating or separating from water. Okay. So you can the easiest way to think about these chemical sedimentary rocks is that if clastic rocks are broken up bits of stuff that's been cemented together, this is just the cement. Okay? This is just the cement. Oops. Okay, so these chemical sedimentary rocks, they're essentially just the cement. So if there is an iron cement that's going to cement together some sandstone, if it just hardened as like a big nodule of iron, it would be called an iron concretion. If there was some calcite cement and it hardened up, it would be considered limestone. Okay, if there was some silica that hardened up, we'd have some sort of a quartz, known as a chert or a flint or a jasper or an agate. So some of these actually are used as gemstones. You can cut them and make really beautiful things out of them. Other chemical sedimentary rocks form when water evaporates. So in really shallow lakes where the water is evaporating, like out of the Great Salt Lake, you get all these salt deposits around the outside edges, and salt is the mineral halite. Right? So you can actually get rocks that way too that are a mixture of different things. Okay. Anybody still writing on this one? Everybody got that? Let's remind you. Okay. Here is a fossiliferous limestone, which is technically a chemical sedimentary rock. It's all these little bits of shell. They're hard to see. We'll see some of this in lab. Are welded together. So let's do classification of sedimentary rocks. This is how you're going to answer your next question on your quiz. There's actually multiple questions to this. It wants you to determine what the name of the rock is based on this table. So let's take a look at this table so you understand it. Over here are the clastic sedimentary rocks. Over here are the chemical ones. Now down in lab, you'll figure that out by looking, are there little bits of stuff that it's made up of, or is it just cement? Okay. Most of the chemical sedimentary rocks look a little weird, and we'll see them down lab. So over here, let's say I give you the question of, you've got a clastic sedimentary rock, so you know you're in this table, and let's say that it's made up of very, very fine material, like maybe mud, like down here, like less than 1/256 millimeters, like very, very fine. You would go across this table here, and you have a shale. See how that is? It's really easy to do. Okay. If it's made up of coarse fragments, like over 2 millimeters, we're talking pebble-sized stuff. You can even see in the picture there. And if I look over here, if the gravel fragments happen to be angular, like pointy, then you have a breccia. Okay. So pay attention to the whole table as you read across it. When you do the chemical sedimentary rocks, they're really described by their composition. What chemicals make them up? So if we look over here, let's say we've got a quartz, SiO2. That's the material that has hardened into a sedimentary rock. And there's a little note here. It's very fine crystalline material. I probably didn't put that on there. Maybe I did. and it's very dark colored, you'd have a flint. And like we used to use in flintlock rifles. Okay, anybody confused? If you're looking at the calcite one, the CaCO3, you better read the textures there. Are there visible shells that are cemented together? Is it really fine or coarse crystalline material? Right. Okay. Are they microscopic shells with clay? That would be a chalk. All right. So there are some features of sedimentary rocks that are pretty neat, and they also tell us about how they formed. I put 3 of them up here just because they're unique, and we do find these occasionally here in Indiana. Ripple marks. Where do you think? What environment do you think this rock? This is sandstone with ripples in it. Where do you think it formed? Yeah, probably on a beach, right? So this is like a beach type environment where it got buried and compressed. It could have been a river type environment where it got compressed. It could have been a sand dune type environment. Any place you might expect to find little ripples, that's where that rock's going to form. Glacial striations are really cool. I do find, pretty often actually, I find glacially striated cobbles out here in Clifty Creek, which is neat when you think about the fact that the rock that you're holding in your hand came from, say, Canada and got drug across the ground, and it made these grooves in it. You can see where the glaciers have all this stuff stuck in the bottom of them. And as they move, they sand the rock that they move over top of, and they grind it up. All that flour that they grind up actually is what made the entire Midwest so fertile. It's the reason we can grow corn and soybeans and all kinds of stuff here, because the glaciers essentially plowed off Canada and then dumped it all down here. It's kind of funny. You can actually find placer deposits of gold down here in southern Indiana in a few locations, and it didn't come from here, it came from Canada. The glaciers brought it down, sorted it, and dumped it. So you find evidence of that in these scratch marks in some of these rocks. I think I've actually, just on offhand chance, I just found one of these the other day. Found 2 of them the other day. So I hold those up. You can kind of see, if I hold it and I reflect it in the light here, see the scratch marks on that? In this one too. They're super smooth on one side. And actually, this one's been striated on both sides. So this was probably embedded in the bottom of a glacier and was just dragging across the ground as it moved down here over the course of, hundreds of thousands of years, right? So I'll leave these up here if you guys want to take a look later. It's pretty neat that you can find these right here in Clifty Creek. Turbidites are a unique one. So think of the word turbidity. It means like kind of cloudy, like hard to see through in terms of water. Turbidites are formed from turbidity currents. So if you've got a location like offshore in water, in the ocean or something, and there's a very steep slope somewhere, and there's an avalanche, an underwater avalanche where a bunch of material slips down the slope and gets all stirred up, what's going to settle out first, the biggest stuff or the smallest stuff? The biggest stuff, right? The big chunks. And so what you're looking in this turbidite here, there's a layer, a band of all these big pebbles. And above that, there's some finer sand. And if you could look above that, there'd be a thin layer of really fine silt, like really, really thin stuff up on top. So you can actually see that there was an underwater avalanche there, and all this stuff got stirred up, and then it settled out according to its mass. Okay, let's do metamorphic rocks. Metamorphism means to change form. Just like a butterfly metamorphoses from the caterpillar into the butterfly, some rocks change. And there's 3 main processes that cause this to happen. Okay. Usually to metamorphose some rock, you've got to get it hot and you've got to increase the pressure on it. Okay. Those conditions don't exist on Earth's surface. They're at least a few kilometers deep, which doesn't sound that deep, but it's pretty far down. A couple kilometers down is a pretty good ways. So we're talking about rock underneath mountains. That's where this stuff is happening. Actively forming mountains underneath, a couple kilometers down, and a little further than that into the upper mantle, rocks being metamorphosed. So the first type of metamorphism which you'll want to kind of keep looking here at your quiz. You've got two choices here. This will help you with the first one. Contact metamorphism happens when magma moves into rock. So you've got a bunch of rock underground, and you've got a big chamber of magma. And as the magma pushes its way up, say it's not going to erupt, it just melts its way up through, the rock around the outside of the chamber that's not melted metamorphoses. It changes. Okay. This can take, for instance, limestone, which is kind of a dull gray looking rock, and convert it into this gorgeous white or pink marble because it cooks it. It just kind of bakes it around the outside. That's known as contact metamorphism. Okay. The other major type of metamorphism is known as regional metamorphism. So this is mountain building. This is plate tectonics. When the plates move and the pressures increase and the rocks fold and bend, this is a high-grade metamorphism. So the rocks really metamorphose a lot. And it happens over big scales, like whole areas of the Earth, not just one little magma chamber, but an entire mountain range metamorphosed. Okay, this produces the greatest amount of metamorphic rock. The way that the minerals metamorphose, they line up in little bands because of the pressures on them. Sorry about that. Apparently I screwed you up. Go ahead and throw that in there. I don't remember where that pass came from. So take a look there. You've got your choices. Answer question number 3. Anybody have a question about that? No. All right. The things that cause metamorphism are mostly heat and pressure. Okay? Hot fluids can cause it as well. So you've got to have heat. These are actual chemical reactions that occur in the minerals. They're not completely melted, but they get hot enough that they chemically react with the other minerals that are around them. You have to have a lot more pressure to make this work as well. Okay. So if we look at some metamorphism here, we've got a bunch of layers of material in the bottom of this lake or this ocean here. This is layer after layer of sedimentary rock, right? It's settled. Sedimentary is where the word comes from. There is a lot of pressure on this already because of the overlying weight. Okay, there's pressure from the sides as well and from the bottom. So this stuff is being compressed. It's turning into rock. Maybe it's already rock. Then as time goes by, there's a deformation. Like this part of the earth pushes into this other part of the earth, and it crinkles and crumples. Okay? So it deforms the layers of rock, and these are going to metamorphose. So many times when we look at metamorphic rock, we actually see banding in the rock. You can see the bands, and sometimes even the folds. Another way that things metamorphose is through hydrothermal solutions. When you've got a really hot body of magma, the hot solution of liquid that's just outside of it, like the water that's in the rocks, can move through the other rocks and cause new crystallization, creating totally new and different minerals. So some of our most striking gemstones, some of our weirdest looking minerals that we have come from metamorphism. And I think you guys probably know that inherently if you've watched cartoons and things throughout your lives. If you want to go find gems and minerals and things, typically you don't go to the flat plains, you go to the mountains, right? That's where people like go mining for things. Well, that's because of the metamorphism created all these different minerals. Oops. We've got two main categories of metamorphic rocks. They're called foliated and non-foliated. So just like we had the chemical and the clastic sedimentary rocks, here we have the foliated and the non-foliated ones. The foliated ones, foliage that means like leaves, so these have a banded, a layered appearance. It's a little bit different than sedimentary layering. It's more of a banding. The non-foliated ones don't. They look kind of crystally. They actually look like igneous rocks. Here's an example of a foliated one. This is gneiss. Yes, we have a rock named gneiss with a G, gneiss. It's a very nice rock. You can see the bands where the minerals actually lined up from the pressure. Here's a non-foliated one. This is marble. It kind of looks somewhat igneous, doesn't it? It's crystallized. It doesn't have bands in it like that. So it's a non-foliated one. And finally, here is our classification table for metamorphic rocks. This is the same one that you'll be using down in lab when we go down there to classify the metamorphic ones. And you've seen the sedimentary one, you've seen the igneous one already. Let's learn how to read this. It's pretty similar to the others. What we're trying to discover is the actual name of the rock. Now, they flip this around on you here. The name of the rock is on the left. On the right, don't get hung up on this, is the rock that it came from. So in other words, what did we squish and cook to get this rock name over here? So these are the names you're using in your quiz question. Slate, phyllite, schist, gneiss, marble, quartzite, and anthracite. Anthracitic coal is what this is. So to figure this out, we have two texture classes, the foliated and the non-foliated. If it's foliated, it's something above this line. If it's non-foliated, it's below that line. Then look over at the textures. You can see here, as the foliation increases, if we go from slate down to gneiss, there's a sequence. Slate is very, very fine, platy materials. Phyllite is a little more wavy. It's going to look a little more schistose. It's going to get a little shinier here with schist. And then gneiss has a lot of nice, bigger crystals that are really banded. It's got banding. And there's some comments over here to help you out. Okay. The grain size just has to do with how well you can see those little minerals that are in there. Okay, they're not grains in the sense that the clasts were grains in the sedimentary rocks. Okay, so if you're reading this and you say, okay, I had a mudstone or a siltstone and it got squished and cooked, that will produce slate. Okay. If slate got squished and cooked, that would give me a phyllite. So use the words over here on the left for your answers because the words on the right are what it came from. And sometimes you're continuing to cook a metamorphic rock to make it more metamorphic. Down on the non-foliated ones, we've got marble, quartzite, and anthracite. Those are your choices. Anthracite is anthracitic coal. Okay. It comes when bituminous coal is squished and cooked. So you'll get the anthracitic coal. It gets slightly metamorphosed. It's still real black, looks like coal. It's the expensive coal. This is the really good, useful coal. Bituminous coal is pretty dirty. Bituminous coal is what we mine here in Indiana. We don't have anthracitic coal. We've got some bituminous coal. Anthracitic coal is found in the mountains. Just think like West Virginia out there. Little comments there, some differences in the coarseness of them. Okay, so take a look at your quiz. If you just follow across it, just remember you're using the names on the left over here. Don't use the parent rock names. You're naming them based on the ones on the left. I think that's the last question on your quiz. Once you finish that, you can submit it. If you need to go back, you can watch other parts. There you go.